In the previous videos, we have learned how to determine the rate law of a given reaction using the initial rates and concentration data. However, in reality, measuring the initial rate of a reaction is technically very difficult. In addition, we have to do several experiments to determine the rate law using initial rates. There is an alternate method to determine the rate law directly from the concentration and time data. This method uses integrated rate laws or rate equations. For example, we have the following chemical reaction with one reactant. A moles of A gives product, and the general form of the rate law for the above equation can be written as rate is equal to some constant K times concentration of the reactant, which is A, raised to the power of its order. Let's assume it as N. The rate of the reaction can be replaced with the rate of disappearance of A with respect to time. That is, minus d concentration A over dt is equal to K times concentration of A times N. This is called as the differential form of the rate equation. We can derive the integrated form of the rate equation by rearranging the equation first and then integrating on both sides. I am going to divide both sides of this equation with concentration of A to the power N and multiply both sides of this equation with dt. If I do that, this is what I get. Minus d concentration A divided by concentration of A to the power N is equal to K dt. Let us say at time t is equals to 0, the concentration of A is equal to A naught. This is the initial concentration of A. And let's also assume after time t, the concentration of A is equals to concentration of A sub t. This is the concentration of A that is unreacted or left over after time t. Now, let us integrate both sides of the equation with following limits. For the time, the limits are from 0 to t, and for concentration, the limits are from concentration A naught to concentration AT. To determine the integrated rate laws for the 0, first, and second order reactions, we substitute n is equals to 0, 1, and 2 in this above equation and continue with the integration. For a 0 order reaction, let us substitute n is equals to 0 in the equation that we derived earlier. We have d concentration A divided by concentration of A to the power 0 on one side and K times dt on the other side. The concentration of A to the power 0 is 1. And the integration of d concentration of A is concentration of A with limits A naught to AT. And the integration of dt is t with limits 0 to t. If we apply the limits, we get the following equation. The concentration of AT is equal to minus KT plus concentration of A naught. This is the integrated form of the rate equation for a 0 order reaction. This equation gives us the relationship between 4 different variables: the concentration of A unreacted at time t, the rate constant K, the time t itself, and the concentration of A initial. If any 3 of them are given, we can find out the 4th variable. For example, If we know the initial concentration of A, its rate constant K, we can calculate the exact concentration of A that is left over after time t. In addition, the equation is an equation of a straight line y is equals to mx plus b. So, if we start the reaction, A moles of A gives products, and measure the concentration of A at various time points, and plot the concentration of A on y-axis and time on x-axis, if we get a straight line from this data, then we can say that the reaction is zero order with respect to A. If we do not get a straight line, the reaction is not a zero order reaction with respect to A. If it is a zero order reaction, we can also calculate the rate constant from the equation. As we can see, the slope of the equation m is equal to negative of the rate constant k. The y-intercept is equal to A naught, that is the initial concentration of A. For the first order reaction, we substitute n is equals to 1 in the earlier equation and integrate it. The integrated rate law for the first order reaction comes out to be ln concentration of AT is equals to minus KT plus ln concentration of A naught. This equation again gives us the relation between the concentration of A at time t, the rate constant K, the time t itself, and the concentration of A naught, that is the initial concentration of A. If any three of them are given, we can find out the fourth variable. Next, this looks like an equation of a straight line y is equals to mx plus b. So, if we start the reaction, A moles of A gives product, and measure the concentration of A at various time points, and then calculate the ln concentration of A and plot ln concentration of A on y-axis and time on x-axis, if we get a straight line, then we can say that the reaction is first order with respect to A. If we do not get a straight line, then the reaction is not a first order reaction with respect to A. We can also calculate the rate constant from the equation. If we compare both these equations, we can say that the slope of the equation is equal to minus k, which is the rate constant. The y-intercept is equal to ln concentration of A naught, from which we can calculate the initial concentration of A, that is A naught. For the second order reaction, the integrated form of the equation looks like the following. 1 over concentration of AT is equal to KT plus 1 over concentration of A naught. Again, this looks like an equation of straight line y is equals to mx plus b. So, if we start the reaction, A moles of A gives products, and measure the concentration of A at various time points, then calculate 1 over concentration of A, and then plot 1 over concentration of A on y-axis and time on x-axis. If we get a straight line, then we can say that the reaction is second order with respect to A. If we do not get a straight line, then the reaction is not a second order reaction with respect to A. If it is a second order reaction, we can also calculate its rate constant from the slope of the equation. In this case, the slope of the equation is equal to the rate constant. the y-intercept of the straight line is equal to 1 over initial concentration of A. Let us now summarize all these three equations. For the zero order, it is concentration of AT is equals to minus KT plus concentration of A naught. For the first order, it is ln concentration AT is equals to minus KT plus ln A naught. And for the second order, the equation is 1 over AT is equals to KT plus 1 over A naught. All these equations give us the relationship between four different variables: the concentration of A after time t, the rate constant K, the time itself t, and the concentration of A at the beginning. If any three of them are given to you in a problem, we can find out the fourth variable. If we want to determine the order of an unknown reaction, we start that reaction and we measure the concentration of the reactant at various time points and plot three graphs. The first one, concentration of A at time t versus t, and if you get a straight line, the reaction is a zero order reaction. If ln concentration of A versus t gives a straight line, then it is a first order reaction. If 1 over concentration of AT versus time gives us a straight line, then it is a second order reaction. Let us do one more example. For the first order reaction, A gives B. The rate constant K is equals to 16 per second. If we start the reaction with 1.0 molar A, how long it will take for the concentration of A to reach 0.45 molar? Let us first write down what is given in the problem. It is given that the reaction is first order, and we also know the rate constant, which is 16 per second, and it's also given that we are starting the reaction with concentration of A is equals to 1.0 molar. That is, concentration A naught is equal to 1.0 molar. And we also know the concentration of A unreacted after time t, that is, AT is equals to 0.45 molar. And we need to calculate the time it takes for the concentration of A to become 0.45 molar. The integrated rate equation for the first order reaction is ln AT is equals to minus KT plus ln A naught. It connects the four variables A naught, AT, T, and K. We have three of them and we need to find the fourth one. Let us plug in the values. AT is 0.45 molar, K is 16 per second, time we need to calculate that, and concentration of A naught is 1.0 molar. Let us subtract ln 1.0 molar on both sides. We get ln 0.45 molar minus ln 1.0 molar is equal to minus 16 per second times t. Let us simplify that. We know that ln A minus ln B is equals to ln A over B. So ln 0.45 molar minus ln 1 molar is equals to ln 0.45, which is equals to minus 0.799. That is equal to 16 per second times t. The negative and negative gets cancelled. If we solve for t, we get 0.0499 seconds. Let us do an example problem. For a hypothetical reaction below, AB dissociates to give A and B. The concentrations of AB, the reactants, are collected at various time points. The data collected in the lab is shown below. Determine the order of the reaction with respect to AB and calculate the rate constant of the reaction. Okay, I have actually transferred all the data into an Excel file. Here I have time and the concentration of AB at various time points. As you can see, AB is a reactant and its concentration is decreasing with time. Now what I'm going to do is, I'm going to plot three graphs. The first one is AB versus time. The second one is ln AB versus time. And the third one is 1 over AB versus time. So first let me calculate ln AB. So these are the values of ln AB at various time points. Next, let me calculate 1 over AB. So these are the values for 1 over AB. Okay, now I am going to plot three graphs. The first one is between the concentration of AB on y-axis and time on x-axis. Let me make that a scatter dot plot. Next, I'm going to add a trend line. Let's also show the R-square value. As you can see, the data does not fit a straight line. Next, let me draw another plot or graph between the time on x-axis and ln AB on y-axis. Again, let me change that into scattered plot. So this data looks okay, but still it's not a proper fit for the straight line. Let me draw the third graph as well. One over AB on y-axis and time on x-axis. As you can see, the 1 over AB concentration on y-axis and time on x-axis gives us a perfect fit for a straight line. Therefore, we can say that the reaction is second order with respect to AB. Next, let us calculate the rate constant from the graph. We know that for a second order reaction, the rate constant is equal to the slope of the line when 1 over AB is plotted against time. Let us find the equation of the straight line. So the equation of the straight line is equal to y is equals to 0.0226 x plus 1.05. So the slope here is 0.0226. which is also equal to the rate constant. And since this is a second order reaction, the units of the rate constant are molar inverse, second inverse.